So today's lesson is a continuation on simple harmonic motion. This pretty much covers topic 9.1. Okay, in particular, we're going to be looking at graphs today and the various energy changes that are associated with simple harmonic motion. And the energy changes and the defining equation of SHM are the two biggest takeaways from this unit. Okay. You may recall, there are a lot of formulas, but some of these formulas we've seen before, and the rest we can get via substitution. Okay, 1/2 mv squared. Well, if we look at what the formula for velocity is, we can get the formula for kinetic energy and total energy from those. And I'll show you that. Okay. So mathematically, the formula for simple harmonic motion comes down to that the acceleration is proportional to the change in displacement, okay, but opposite. That's what the minus sign is. If I want to make it an equal sign, okay, my acceleration equals, I can multiply the delta x by some coefficient, okay. I've been using the letter capital K for that, okay, and this equation is the key to simple harmonic motion, okay. You have to remember this formula and remember what the minus sign means. Okay, and so in simple harmonic motion, energy gets converted back and forth from kinetic energy to potential energy. For a pendulum, it's gravitational potential energy as it swings up and then back down. At the bottom is where I'm going to have my greatest kinetic energy, and then it swings back up. At the peak, my velocity has stopped, and so my kinetic energy has gone to zero, but I'm at the highest point, and so that's my greatest potential energy. Okay. Ideally, and that's the type of system we're going to work with mostly until we get to the engineering option, ideally the total energy is going to be conserved the whole time. We don't lose any energy due to friction or air resistance or anything like that. Okay, and it's important to remember where we experience those minimum and maximum points for energy, velocity, acceleration. Okay, and at the amplitude points, okay, looking at a mass spring system now, at the amplitude points, my potential energy is a maximum. This is true for every single type of simple harmonic motion system. And at the equilibrium point, my kinetic energy is going to be a maximum, okay? At that point, okay, remember, I'm at equilibrium. There's no forces to either direction, really, okay? So at that point, my velocity has reached its maximum, and therefore my kinetic energy is at a maximum. Okay, I put together this table to remember when I hit 0 points and maximum points. It's worthwhile to try and memorize this, or at least be able to derive it. At this point, I'm able to derive this table in less than 20 seconds, largely based off of definitions and visualization of what happens either in a pendulum system or in a mass spring system. Okay, so generalizing energy, so I can think about it at other points besides just the amplitude points or at the equilibrium, okay, I come up with these set of formulas, okay. At the amplitude point, my kinetic energy is going to be 0, but my potential energy is this maximum, okay. If I call x sub 0 my amplitude, then my potential energy becomes 1/2 k x 0 squared. I would have a similar minus x 0, but as long as I square it, it comes out positive, okay. So because total energy is the sum of kinetic and potential, my total energy must also be 1/2 k x 0 squared. Okay, so at some arbitrary point x, my potential energy is 1/2 k x squared, and my kinetic energy is the difference between my total and my potential energy. Okay, going through the formulas to solve for velocity at that point, I find out that my velocity is based off of omega and amplitude and position. Okay, and it's this formula plus or minus the omega square root x0 squared minus x squared. Okay, plus or minus because at one point I'm going to the left, at the other point I'm going to the right. Okay, and as long as I know what omega is, okay, and I can solve for this thing. So omega is a very key variable to try and derive in most of these situations. So generalizing that, okay, if my velocity is equal to plus or minus omega square root x0 squared minus x squared, okay, remember the squares are inside. If you need to look up the formula, please do so, okay. And so my kinetic energy is going to equal 1/2 m omega squared x0 squared minus x squared Total energy we've already talked about, and potential energy as well. Okay, just a matter of sticking in my values for X, for total energy and stuff like that. So it's important to be able to figure out or calculate what omega is from various situations. Okay, and so you're going to run across multiple graphs. Okay, and we're going to have graphs both in the time axis and in the position axis. Okay, and we need to be able to pull omega from these graphs. Okay, so the kinematic graphs of displacement, velocity, acceleration. Okay, we're going to be getting our period from the time axis, and as long as we have the period, we get frequency, and if we have pre-frequency, we have omega, because omega equals 2 pi f, okay, or 2 pi times the frequency. Okay, when I get an energy time graph, again, as long as I have time, I can get period, but you have to be careful with the energy graphs. Okay, because they're sine squared graphs, you need to remember that I get two hills and valleys in the picture before I get to period. Okay, so you need to be a little bit careful. I can't do it off of a total energy graph because it's just a flat line, and I can't get any information out of a flat line. Okay, but you have to remember you have to go two hills and valleys to find the period t. And you have to remember that energy graphs will always be positive. So double check your axes and look for information like that. Okay, for position graphs, okay, we end up with a little bit different set. Okay, we'll end up with force graphs. Okay, in this case, this is the force associated with the spring. Okay, but all simple harmonic motion graphs will have a very, very similar graph. Okay, in this case, if my the slope of this graph happens to be my spring constant k minus k, to be honest, but that's because my force is opposite the displacement as well. Okay, to get omega, I'm going to need to know what my mass happens to be. Okay, because once I have mass, I can get acceleration from there, or remember that omega is equal to the square root of k over m. Okay, so if I have an acceleration displacement graph, my slope is that k over m, or that omega squared. Remember to take an absolute value, okay? It's minus omega squared. Okay, we'll also run into energy graphs for position, and we can get a lot of information from these as well, okay? Because my total energy, okay, or maximum energy for either the kinetic or the potential, okay, my total energy is 1/2 m omega squared x0 squared, or my amplitude squared. Okay, I can read my amplitude from this graph as well, because at that point, my kinetic energy has hit 0. Okay, or at that point, my potential energy has hit its maximum. Okay, and again, I'm going to need mass to get to my omega, okay, from these graphs. But I can calculate omega, and from there, make my other calculations using the formulas. I don't recommend necessarily deriving these formulas. I think they take a little bit longer. We're not as familiar with them, so it's worthwhile to know where they are. These are all in topic 9.1 in the data booklet. Thank you.